Hi everyone, so in our last video we began to have a gentle introduction, I hope, to general relativity and what it's got to do with transformations between reference frames. And after a little bit of discussion about inertial mass and gravitational mass and how fundamentally there's no obvious reason why they should be the same, we know that from empirical observation they are the same. So place any two objects in the same gravitational field, they will experience the same acceleration. And I was saying that for hundreds of years, so from Newton until Einstein, no one really knew why that was true. They just knew that it was true, to the best of our knowledge. But it was really a stroke of genius from Einstein that explained why it's true. And I was reminding you from your study of classical mechanics, if you did it, what a fictitious force is. So a fictitious force is a force that you introduce in a non-inertial frame if you want to just artificially make Newton's laws apply in that frame. And we began then to look at this example of a free-falling ball. So just a ball just falling freely under gravity. We were saying that in Newton's picture, if you are standing on the earth and just watching the ball fall, then according to Newton, that's because there is just a mechanical force of gravity pulling the ball down. So it's the gravitational mass times the acceleration due to gravity. And then if you switch to the frame where you fall with the ball, then you don't see the ball falling. Okay, so the ball will be at rest if you fall with the ball. It will appear to you to be at rest in that frame. But the force of gravity is still there in Newton's theory, so you introduce a fictitious force, equal and opposite, pointing up the way to counter it. But Einstein said, well, actually, if you think about it, if you're in this situation of free fall, so if you are the ball, you can't actually feel either of those two forces. Okay, so if you just, and I mentioned about the space station, you know, the astronauts in the space station, why do they appear to be weightless? It's not because they're so far away from the Earth that the gravity is negligible. It's simply because they are in free fall. Okay, now, Einstein's thought then, what he called his happiest thought, in fact, was that since in the situation where I fall with the ball, since I can't actually detect either of these two forces, it's simpler just to think about it as they're not there. So in the frame, this is Einstein's picture, in the frame where you fall with the ball, there are no forces. Okay, and in the other frame then, where you're standing on the earth, the reason that you see the ball fall is not because there's a mechanical force pulling it down, but because there's a fictitious force that appears to be pulling it down. So Einstein said, really, in Newton's theory of gravity, you've got inertial and non-inertial the wrong way around. Okay, so remember I said last time, how do you know if you're in an inertial frame or a non-inertial frame? You will know because in an inertial frame, you will not have any fictitious forces. Okay, so Newton's laws do work in the inertial frame, but in the non-inertial frame, you need to introduce fictitious forces. And so in Einstein's picture, in the frame where you fall with the ball, there are no forces, and the ball appears to be at rest, so that is the inertial frame. It's this other frame, the Earth frame, so where you see the ball accelerating, but there's no mechanical force anymore of gravity. Einstein says you introduce this fictitious force that appears to pull the ball down. And so you can see that by a change of reference frame, I can actually make gravity disappear completely, according to Einstein. So here, in the Earth frame, gravity appears as a fictitious force, but then by transforming frame to the ball frame, it just disappears. Okay, and you can do that with an object moving in any uniform gravitational field. Okay, uniform meaning we just assume it's in the same strength, it has the same strength and in the same direction everywhere, which is roughly true near the surface of the Earth. Okay, over a small region of the Earth's surface. So this was what Einstein said. Gravity is a fictitious force. By transforming to a free-falling reference frame, in other words, the frame that falls with the ball, a uniform gravitational field can be made to disappear. And now moving on from last time, by the same token, by changing reference frames, you can also create artificial gravity. Okay, and you can create an artificial uniform gravitational field. So you imagine a space rocket, okay, as I've drawn here. And imagine you're standing inside a space rocket. Okay, so just imagine you're standing on the floor of it, and you feel, imagine that you just feel like normal gravity. Okay, so don't imagine that you're floating around weightless. Imagine you feel what you think at least is normal gravity. So you're just standing on the floor. Now, one possibility for why that is the situation on the right. Okay, the rocket is just parked on the launch pad at Cape Canaveral, and you're just standing on the floor of the rocket. Okay, so it's just the Earth's gravity keeps you there. Fine. But there's another possibility. There's another possibility, and it's that actually your rocket is in deep space, and it's far away from the Earth. Okay, so far away from any large mass, so far away from any planet or anything that creates a gravitational field. So just in free, empty space. But the reason that you feel that you're standing on the bottom of the rocket is because the rocket is just firing its engine, and the rocket is accelerating uniformly in this direction. Okay, so in the direction that then pins you to the floor. Okay, so you feel like there's a force of gravity. Okay, so the rocket accelerates with 9.81 meters per second squared, like this. And if that's the case, to you inside the rocket, you will just be standing on the floor. Okay, so it just feels very much like artificial gravity. Okay, in fact, if you really did this, okay, so if you really did stand on the rocket, and assuming that you couldn't hear the sound of the engines or whatever, there's actually no way to tell which of these two situations you're in. Okay, if you can't see out the window or anything, you actually couldn't know. So this is a way that you can also create gravity by changing reference frame. Okay, so in this situation, if you're the rocket in deep space, so if you are an external observer, so if you were someone who's outside the rocket, hopefully in a spacesuit, you would be able to see the rocket accelerating along with respect to maybe other things in the background, like with respect to other planets or objects or whatever you can see in your field of view. But if you switch then to the frame where you're the guy or the girl inside the rocket, you wouldn't know. Okay, so in that reference frame, it's an accelerating reference frame, and you can artificially create a uniform gravitational field. So that's what Einstein says. Okay, uniform gravitational fields, they are the same as just a choice of reference frame. Okay, and it's kind of crazy to think that gravity is just a fictitious force. Okay, so the reason that your feet stay on the ground is really just a choice of reference frame. Okay, or in the mathematical language, it's a choice of coordinate system. Okay, it's a choice of coordinate system. And that's the equivalence principle. Okay, so the equivalence principle says that a uniform gravitational field, as we saw here in this example, it isn't really a force. Okay, it isn't really a field. It's just a particular choice of reference frame. Change the reference frame, it disappears. Okay, or change the reference frame, and you can create an artificial gravitational field, a uniform gravitational field. Now, it may feel that this is not very convincing. Okay, it's a bit hard to wrap your head around this idea that gravity is not real. It's just kind of an illusion. And in particular, when it comes to non-uniform gravitational fields, we haven't really dealt with that. Okay, so if you think about a planet or a star, yes, the gravitational field looks uniform if you're on the surface, just over a small region, but far away that's not the case. Okay, so you know, if you move further away from the Earth, you know, the gravitational field is non-uniform, and the gravitational force, you know, diminishes as 1 over r squared, so it diminishes with distance, and it's not all in the same direction. Okay, it's like spherically symmetric. So, can a real gravitational field, so to speak, can that be made to appear or disappear by a change of reference frame? And the answer is yes and no. It can be made to disappear locally. Okay, so that's what I say here. So back in the last chapter, although I didn't really cover this in the videos, but we began to talk about curved spaces. Okay, so non-Euclidean spaces. And that is something that cannot be overcome by a change of reference frame or a change of coordinates. So if a space is curved, i.e. non-Euclidean, then it is just non-Euclidean and that's it. But it turns out that if you just look at a very, very small piece of a non-Euclidean space, then it looks almost Euclidean, almost flat. Okay, so think back to the example of the surface of the Earth as a non-Euclidean space, the surface of a sphere. Yes, if you stand and look at it from the outside, okay, so maybe you're Neil Armstrong and you're standing on the moon and you're looking at the Earth, yeah, you can clearly see that the surface of the Earth is a non-Euclidean space. But for us standing on the surface of the Earth, and for us that can only see a small piece of it, okay, so we can look out our window and maybe we can see a couple of miles. What we can see, it doesn't look curved to us, right? It just looks flat. It does look Euclidean to us, and that is because we are only looking at a small piece of it. Okay, so if you have a non-Euclidean space, if you just take a very small piece of it, it does look Euclidean over a small neighborhood. Okay, so to put it more mathematically, if you pick a particular point P in your space, it is possible always to choose a very particular coordinate system, and this coordinate system is defined like this, okay? And you can look back to chapter 3 if you want to, okay? Look at the section, pardon me, chapter 4, okay, so tensor calculus. Look back at the section in the notes called geodesic coordinates, okay? And that's what these coordinates are. So here the gammas are the Christoffel symbols, okay? I don't want to get too much into details here, and it's not important for you to know the details inside out. Okay, so if I wanted you to do something with these coordinates on a test or an exam, you know, I would give you this formula. But it turns out that if you construct a new coordinate system using this formula around a particular point P, okay, so these x subscript p's are like the old coordinates of that point, and then we transform to these new barred coordinates. Turns out that all the Christoffel symbols in these new barred coordinates, they vanish at the point P. Okay, so the Christoffel symbols in these new coordinates are 0 at the point P, and that means these new coordinates are like Cartesian coordinates at the point P. Okay, so remember, in Cartesian coordinates, all the Christoffel symbols are 0. Why? Because the basis vectors don't depend on position in Cartesian coordinates. Okay, in Cartesians, the basis vectors are the same everywhere. So their derivatives are non-zero, so the Christoffel symbols, their derivatives are 0, so the Christoffel symbols are 0. Okay, so in these geodesic coordinates, turns out Christoffel symbols are 0 at this point P. So it's like you can use Cartesian coordinates, but really just at this one point, okay? But locally, the space is almost flat, almost Euclidean around this point P. So that being the case, if you have a non-uniform gravitational field, no, you can't make it disappear everywhere by a change of reference frame, but you can make it disappear locally. So a small region, in a small region of space, the gravitational field will be almost uniform, okay, and you can make it disappear. Or similarly, you can make an artificial gravitational field appear in a small region of that space. Now, this brings us on to, again, what curvature has got to do with gravity, okay, and or what non-inertial frames really have got to do with gravity and with curvature in space. So what we're going to do here, just to finish this video off, and to finish our introduction to general relativity before we get into the heavier maths with the tensors, we're going to look again at an example of a rotating frame of reference. Okay, so this is a bit like the rotating bucket that we had last time. It's the same example really. Okay, so let's just imagine here that we have a disc that's rotating. Okay, so this could be like the roundabout at the play park, the merry-go-round, could be the hobby horses at Barry's, if Barry's was still open, whatever. Okay, a rotating disc. So it rotates with angular speed omega, and it has a radius r. Okay, fine. And let's think about two different frames of reference. Okay, so let's have, first of all, the frame of reference S, where you are just standing outside the hobby horses, watching them rotate. Okay, and your frame then is inertial. Okay, you are not accelerating, it's the hobby horses that are accelerating as they go round. And then let's think about another frame of reference, S bar, where you are on the hobby horses, riding them. Okay, so you're going round and round with the hobby horses. So in your frame of reference, it's not the hobby horses that are rotating, it's the entire rest of Barry's building that's rotating around you the other way. So at any rate, here's what we're going to do. We're going to measure the radius and circumference of the hobby horses platform that they're on, okay, that 100-year-old wooden platform. Okay, fine. So how can you do that in principle? So you can just take a big ruler, okay, or maybe a better way you can think about it is imagine you have like a set of rods, okay, so metal rods or wooden rods of a fixed length. So maybe you have a bunch of rods that are each, 1 inch long, okay, and how you can measure this radius or this circumference is by taking these little 1 inch rods and laying them along this length. Okay, so you can imagine taking these rods and just placing them along and then counting how many you need. Okay, so if you need 40 rods, then that means the diameter is 40 inches. Okay, for hobby horses, obviously it's a lot more than that, but you get the idea. And you can do the same for the circumference, okay? So, if you take them small enough rods, okay, then you can lay them out and get pretty much, you can't lay them, they're not circular rods, but if you have them small enough and you use enough of them, then you can lay them out along the circumference of the circle and measure the circumference too. So do this in both frames of reference. Okay, so they're the same rods, but look at the measurements from both frames of reference and what will happen. Okay, so let's first of all do it in frame S. Okay, so where we are outside the hobby horses, watching the hobby horses rotate. If you do that, okay, you get two measurements. Okay, so let's just call the radius C, or sorry, call the radius R, and the circumference C. Fine, nothing fancy there. And in that frame, you will find C equals 2 pi R. Okay, no problem. And that is a familiar formula from Euclidean geometry. Okay, so C equals 2 pi R. Okay, that's what you'll find. Yeah, nothing profound there. Okay, so now let's change to the frame S bar where we're rotating with the hobby horses, and we can do the same thing. Okay, so take those same rods, lay them on the radius, lay them on the circumference, and we get two measurements. Okay, so let's call them R bar and C bar. And it turns out that what will happen is that you don't get C bar equals 2 pi R bar. Okay, what? How can that be? Okay, how can the circumference not be 2 pi times the radius? Well, it all comes back to length contraction. Okay, now as that hobby horse spins round and round, those rods, okay, if you lay them out along the radius, the direction of motion is perpendicular to the lengths of the rods, okay? So that's fine. Nothing happens there to do with length contraction. So you will find that the two measurements of the radius are the same. But on the other hand, the rods that you lay along the circumference, length contraction does have to be considered for those, okay? So as the hobby horses rotate, those rods are moving in the direction along their length, okay? And so that means that if you are in frame S, okay, if you are in frame S where you look at those rods and you watch them rotate, okay, so in the frame S these rods appear to be moving with a certain velocity along their length, then they will contract, okay? So the circumference will actually appear to be smaller in frame S than it appears in frame S bar. Okay, so in frame S bar, where you rotate with the hobby horses, then the rods on the circumference don't appear to be moving. Okay, so they don't contract. But in the frame S, where you watch the hobby horses rotate, then those rods do contract. So, you know, rather than them being an inch each, they're something less than an inch, but you still have the same number of them, okay? You haven't touched them. So the circumference actually gets smaller, okay, by a factor of 1 over gamma. So this is the relationship between the two measurements of the circumference. So the circumference in S, which we call C, is equal to C bar divided by gamma, where gamma is the Lorentz factor, okay, evaluated at velocity v, where v is just omega, the angular speed, times the radius r. So that might seem a bit crazy, but this is what we find in the frame S bar. The circumference, C bar, is not just 2 pi r bar, it's 2 pi times gamma r bar. Okay, so that comes from this equation here. Okay, so this C with the not bar is 2 pi r, and r is the same as r bar, so if you multiply through by gamma, you get C bar equals 2 pi gamma r bar, and that's always greater than 2 pi r bar. So in the non-inertial frame, Euclidean geometry doesn't apply. Okay, so in the non-inertial frame, it looks like the circumference of a circle is not just 2 pi times its radius. And that means that in the non-inertial frame, it acts as if there is curvature in the space. Okay, so there's an example in the notes way back in chapter 4 where I show that in non-Euclidean spaces, familiar formulae for Euclidean geometry don't apply anymore. So in the example of like the surface of a sphere as a non-Euclidean space, you'll find that, you know, the same thing here as here. So the circumference of a circle isn't 2 pi times the radius. And the same thing happens here. So when you're in a non-inertial frame, then you get, apparently, curvature of the space. Okay, so non-Euclidean geometry holding. And when are we in a non-inertial frame? When we have fictitious forces. Okay, in other words, when we have gravity. And this was Einstein's, again, stroke of genius. Okay, that the presence of gravity, so if you have a frame of reference where you think there's gravity, that means that your frame of reference is really non-inertial, and then that means that your space is actually non-Euclidean. Okay, there is curvature. And this, so we finally now get to the big idea of general relativity. This is the idea, and this is just a postulate, okay, but Einstein dispensed with Newton's theory of gravity and came up with this. And it's that, how does gravity work? So why is it that if you have masses, they appear to attract each other? How is that force even communicated? So that, which was something Newton couldn't explain. You know, how does the sun talk to the Earth? Okay, they're separated by like 92 million miles or whatever. So how do they talk to each other? And Einstein gives the answer here. They don't. Okay, it's just that the fact that they have mass causes space-time to become non-Euclidean. And so motion in a so-called gravitational field isn't really in a gravitational field. Okay, the gravity isn't really there. It's a fictitious force. It's not a real force. It's actually just free motion. Okay, so the Earth isn't really moving in a gravitational field produced by the sun. It's moving freely. Okay, the Earth is moving freely with no forces. It's in free fall. It's just that the motion takes place not in flat space-time, but in curved, non-Euclidean space-time. And the key idea is that what does a particle, so what does a planet do if it's moving freely in curved space-time? Well, remember back to your Newtonian mechanics. If you have a particle, like a planet, with no forces acting on it, free motion, how does it move? Well, first law says either it's at rest or it moves with constant velocity. In other words, in a straight line. Okay, so particles or planets with no forces on them should just move in straight lines in Newton's theory. So why doesn't it happen in Einstein's theory? So Einstein says, yes, the Earth is moving freely. There are no forces. It is moving in a straight line, so to speak. it's just a straight line in curved space-time, non-Euclidean space. Or to put it more precisely, in a non-Euclidean space, there are no straight lines. So the planet can't move in a straight line. It moves in the closest possible thing to a straight line. And what's that? It's a geodesic. Okay, and that's why we were so interested in geodesics and Christoffel symbols before. This is how motion under gravity really works, according to Einstein. So a planet or a particle moving in a so-called gravitational field, it's really just moving freely, so there's no force, and the frame of reference that moves with the planet is inertial, the free-falling reference frame. It's just that this motion is in curved space-time, so the planet doesn't appear to move in a straight line anymore, rather it moves in a geodesic. And that is Einstein's theory of general relativity in a nutshell. So in the next video, we're going to get started into the mathematics of all this, and Einstein's field equations, and so on.